We have covered so far what's called the first derivative test. When you take the derivative of a function, the first derivative tells you if the function is increasing or decreasing. That's what we've spent all this time doing. Increasing or decreasing. It also tells us these critical points, where at those critical points we may have relative max or mins. Okay, so the first derivative will always tell you if the function is where it's increasing and decreasing, and if you have a relative max or min. So at every time on the homework or even on the test, when I say something like, find where the function is increasing, take a first derivative. Find the possible max or min, take a first derivative. Are you with me on that? First derivative, increasing, decreasing, finding relative max or mins. Today, we're going to talk about what the second derivative does. Okay? The second derivative actually helps us determine where the function is concave up or concaving down. And I'll explain what that means in a minute. Concave up or concave down. It also helps us find possible inflection points. So you have to really pay attention to the directions on homework. If the directions say, find a max or min, only have to take a first derivative. If the directions say, find possible inflection points, you got to take a second derivative. If the directions say, find out where the function's increasing, first. Directions say, find out where it's concaving, second. You with me on this? That's why you've got to know these words and how to put them together. All right, so let me explain what this idea of concavity means. Concavity. Concavity is the property of curving upward or downward. The property of curving upward or downward. So before I show you what it looks like, just make sure you write this down. If you take a second derivative and you find out that the derivative of the function is positive all the time, do you think it would be concaving up or would it be concaving down? Positive. Up. Okay, positive. If the second derivative is negative, then obviously it should do what? Concave down. Okay. Now, what does this look like visually? And this is what I'll give you this picture, and then I'll give you this picture, something like that. Okay. I want you to think of concavity. It's the where it curves, and it's curving upward or curving downward. And I think that was hard when I first remember teaching this. And then finally I found something and I made a little bit more sense. It was like where it holds water or where it spills water. So here's what I mean. Okay. Right here, if I'm following this graph, this part of the graph would spill out water. Okay. Up until about this point, which it would right now if I was pouring water, like making it rain, you know, that game. Judah plays it all the time.
You mean the one where you flip the money?
Yeah. Why is he obsessed with that? I have no idea.
Cup and you have to draw, like, you know what I'm saying?
Yeah, I know what you're saying.
Oh, yeah. The little dinosaur.
No idea what you're talking about. No idea. No idea. But now we've started a whole new bad part of this lesson.
And you have to draw the bridge. Like, I get those ads all the time.
Okay. So do you see the difference here? Like this part of the graph would actually spill out the water, whereas this part of the graph would like hold the water.
It's not the same.
So this is, I have no idea. This is concave up, whereas this part right here, the graph right here to here, this is concave down. This part of the graph is concaving up. This part of the graph is here. That point right there where they change from down to up or up to down, that point is called a point of inflection. That point where you change from concave up to concave down is your point of inflection. No way. So let me do it again on this picture. So what do you think this part of the graph is doing?
It's gonna be.
It's concave up. Look, it's holding water right until about probably here. Okay, not at the max, not at the min. Right about here. And then what does it do after that? Then it spills out the water. It switches from now it's concave down, and then here it's concave up. The curving is an upward. And again, that point right there is your point of inflection. All right? And that's what we're going to be, that's what the second derivative determines for us. Just where the graph is being really curvy up or really curvy down. That's all it's doing for us. All right, but I do want you to write this little definition down, which is the definition for point of inflection. Point of inflection is a point on the graph, where it changes from concave up to concave down, whoops, or vice versa, concave down to concave up, or vice versa. Okay, point on the graph where it changes from a concave up to a concave down, or vice versa. Does that make sense to you, kind of? I hope. I mean, and by the way, do you always, it's kind of like that disco graph always has a concave, up or down kind of thing, these disco graphs. But they can actually occur in like cubics and, cortex and stuff like that. So I'm going to do the last two problems of your homework tonight, okay? And I don't want to say they're hard. They're just, a little bit more challenging. Again, it's not getting harder, kids. You're getting smarter. That's right. That's right. Remember it. Thank you. Autumn Calabrese. I'm going to actually write down what the directions say for both of these problems so you can understand what we have to do, and then we'll do the actual problem. So the directions say the same thing. Find the intervals on which the graph is concave up or down, and identify all extrema. And here's your function. F of x equals 2x to the fourth minus 8x plus 3. I'll give you a minute. 42 is the same instructions. Okay. This is, again, why this is the law. Years of me teaching, I learned so many things. Because I remember when I first taught this, poor Ben's class, poor Ben. Because they were the ones who never did these last two problems because they got so tired. But this problem has a lot in it. Here's why. It just stopped right here. If it just said, find the intervals on which it's concave up or down, you just have to do second derivative, and that's easy. But it says identify all extrema. Boo. Now we actually have to go back and do the first derivative also and determine where the increasing, decreasing is. So I'm doing it for you. I'm sorry. The words should come out of your mouth. Thank you, Aseta. Thank you. I appreciate you going to all this trouble. OMG, OSH. I cannot believe you people. Same thing. All right. So concave up or down. We're going to start there. So we're going to do a first derivative, because in order to do a second derivative, got to do a first derivative. Okay. What's the first derivative? Okay. I'm just going to leave a little room because I'm going to have to go back to this anyway, unfortunately, because that's the way the question is. But I'm going to do my second derivative right now. What would be my second derivative? Okay. Equals 0. Why am I sending it? Because you're literally doing the same thing you've done before. You're finding a critical number now at the second derivative to determine if it's a point of inflection. That's what you're just doing. Okay. So what would be my critical number at the second derivative?
0.
X equals 0. You're going to create still that little number line x-axis. I'm actually going to go like this. Okay, I'm going to put 0 here. I'm still going to do what I did with the first derivative. I'm going to test a number that comes before 0, but not in the first derivative, not in the original, in the second one. So if I plugged in -1 right here, what happens when you square -1? So it's positive. So that positive doesn't mean it's increasing. It means the function is concaving because we're in the second derivative. All right, now we plug in a 1. What happens here?
It still goes up. It goes up.
Oh, so if I were to read the directions, find the interval which the graph is concave up or down, I would say it is, no, I would say it's concaving up, negative infinity. So here's your part of your,
That's it.
Am I right?
no, the second derivative is a parabola, yes, but it's not, it originally is not. This function right here is concaving up the entire time. It is concaving up the entire time. Okay? Now, here's my question. Is this a point of inflection? Why no? It didn't change from up to down or down to up. So you can, we're going to find out. This is not, I should say not a POI. POI stands for point of inflection, not a POI. If it went, can it be? No. In order to be a point of inflection, you have to concave up to down or down to up.
Well, yeah, like, will that ever happen? What?
It just never happened in history.
Yeah, it never will. Okay, that's why I was asking. It never will.
All right. So we've done the first part of this homework here, the directions, which say to determine where it's concaving up or down. Now we have to identify all the extrema. To do that, anything that deals with extrema is a first derivative. We already took a first derivative. We're going to set it equal to 0 and do what we've been doing now for days. Factor out an 8, x cubed minus 1 equals 0. What is my critical point? 1. Make a first derivative number line. Put 1 right here. Plug a number into the first derivative, critical points into the first derivative. So if I plug 0, I would get positive or negative. What would I get? Negative, which is, what do I write here?
Decrease.
No, it decreases.
Decreasing because I'm in the first derivative. Good job. What? Plug a number like 2 in to the excuse me, not the original, the derivative. I get a positive, which means I am increasing. Okay, ready? Watch my finger. If I start here and I decrease, then I increase. What is that?
That's a minimum.
That's a min. So I have a min at 1 comma what? Where do I find that what? Plug it into the original. So 2 minus 8 plus 3. This is there is one relative min at 1, -3. There is no points of inflection. It is concaving up the entire time. If you were to plot this on your graphing calculator, which I think I did have, but then I erased it. Let me actually see if I still, I did. 2x to the 4, I know, right? 8x plus 3. Let me turn this one off. 6. It's coming. There you go. There's the original function. That's 2x. I don't know, remember if you recall from last year, you should, that quartic functions can actually look like quadratics. Do you remember that?
Yeah.
So this is a quadratic right here at 0. It slants, but it actually never changes from its concavity. It never makes that little like cubic dip right there. But it is a quartic, yeah. So look at that. It is concaving up the whole entire time. It goes from a decrease to an increase, and there is a min right there. Yes.
When you make the graph, like, when do you make it, when you plug in the points from the table?
Yeah. That's for absolutes.
I just read the.
Oh.
We don't need to find absolutes.
Oh, okay. Cool.
Yeah. All right.
Shake it back.
42. Now this one's our hardest one, and then we'll be done.
Yeah.
All right, the directions, by the way, are the same for this one, so that's why I'm going to do it for you real quick. All right. You ready? You ready? Ready? Here we go, yo. Take a first derivative of this function, my children. Product rule. And chain. First times, what's the derivative of the second? 3x plus 2 to the second times the chain inside, which would just be what? 1. So I'm not going to write it. First times the second plus the second times the derivative of the first, which is still 1. So I was very kind to you. Now, when I have something that looks like this, I like to factor out what they both have in common from each part. So I'm going to factor out an x plus 2, what power? Put a little bracket. Tell me what I have left. Yeah, 3 times x minus 6, which is 3x minus 18. We'll do that in a minute. And then what do I have plus what here? One of them. Clean this up. 3x minus 18 plus x plus 2. 4x minus 16 times x plus 2 squared. You could factor out another 4, but I'm just going to leave that right there for where it's at. Okay? That's the first derivative, but remember we're trying to find its concavity, so I have to take second derivative. Let's go. Take the product rule of this one, my friends. So here's my first derivative. So what would be the product rule? First times, what's the derivative of the second? 4 plus second times, what's the derivative of that? 2, x plus 2 times 1, which I don't need to write, okay? Now I'm going to factor what I can out from each of these two right here. So do you see how they both actually have, this has a 4, this has a 2? Actually, this actually has a 4 that I could factor out, but I'm not going to. I'm just going to leave it like that. But I'm going to factor out a 2. I'm going to factor out an x plus 2 because they both have that. And then what would you be left with in each of those groups?
X plus 4, x plus.
And a 2, right? Yeah. Plus, what am I left with here? Just the 4x minus 16? And so 2x plus 4 would make 6x, yes, minus 12 times the 2 times the x plus 2. Why am I not factoring all the way out? I mean, you could, but really that factoring out a 3 here doesn't change its sign necessarily. So I'm just going to leave it right here. And I can actually figure out a critical number from here. Can you figure out the two critical numbers right here and here?
Yeah.
What's the critical number here?
-2.
Could you figure out what number times 6 minus 12 would give you a 0? 2, right?
Also 2. 2 and -2.
So 2 and -2 are your critical numbers for the second derivative. Yes.
This is really dumb, and I probably just didn't see it, but on the second half of the product rule, where is the 2 coming from? Like you have 2 times.
Remember the derivative of this would be 2 of that. Yeah. All right. So let's make our little chart here. Remember, we're plugging into a second derivative. We have -2. We have a 2. Okay. I'm going to plug a number that comes before -2, and I'm going to plug it into right here, this factored area. You could plug it back in, but it's better into that one. So -3 would make that negative and would continue to make that negative. And what do 2 negatives make? Okay, so what am I doing here? Am I increasing or is this a concave up?
Okay.
Why?
The second derivative.
Beautiful. You're brilliant. Okay, plug a 0 in. Positive, negative, which is negative, concave down. Positive, positive again. Wouldn't that be? Yes. So concave up. So answer the question. You are concave up from where to where?
-2.
And then where to where?
2 to infinity.
And where are you concave down? -2 to 2. That's the first part of the question. Are any of these points of inflection?
Yeah.
Which ones?
-2.
Both of them are. When you switch from a concave up to a concave down, then a concave down to a concave up, these are both points of inflection. So you have to find them. How do you find them? Well, you know, one of them is going to be at -2, comma something. The other one's going to be at 2, comma something. How do you find that comma something? Plug it into the original. Anytime you want to find a Y value, you plug into the OG, y'all. Plug it into the original. I'm going to give this to you because these are crazy numbers. Well, -2 is not bad, but 2 is -256. Those are your points of inflection right there. That's where it's going to curve from an up to a down. It's going to go like that, okay? All right, and then we just have to answer the other part. Do we have any more extrema? Well, to figure out if we have any more extrema, we got to go back to the first derivative.
This is kind of ridiculous.
And again, what's coming out of your mouth should say, I am so
Thank you, Mrs.
That's right. That's
If I
right.
would have done this, I would have
It
done
was
it.
not got.
I wouldn't have even.
Exactly.
I think it was 42.
All right, let's set this one equal to 0. Tell me where my critical numbers are at.
-2 and 4.
And 4, good job.
What'd you hear?
Okay, now again, we're gonna do -2 and 4. We're gonna determine if we've got something increasing or decreasing. Same thing, positives and negatives. So, let's pick -3. That would make this no matter what positive. So I'm just gonna plug -3 here all the time. So is that what? Negative? So it's decreasing. Good job. Plug in 0 would be negative, decreasing. Plug in 5 would be increasing. So what's -2? Nothing. Actually, we found out what -2 was. -2 was a point of inflection, actually, surprisingly enough. But 4 is definitely a what? Max or a min? There is a minimum at 4, and I'm actually going to give it to you. 4 -432. And I kind of want you to visualize this, so you can graph this for me somewhere here. I'm going to actually give it to you in a better graph. This is a really crazy one. At -2, 0, there is a point of inflection. At 2, -256, there's a point of inflection. I'm doing this terribly wrong. It's going to go off the grid. Let me make -256 like right here. And then at 4, -432, that's the min of the graph. And again, look back at the original. The original was a quartic. So it's actually going to be that W shape. It's going to go like this. It's going to start up here. It's going to do this little dip. It's going to concave up, concave down, and then it'll have a min concaving up the entire time. That looks actually pretty awful inaccurate because of my scale. So I kind of want to show you what it's going to look like on the graph a little bit better here. Hold on. Y equals right there. Let me turn. Oh, come on, Aseta. Let me turn this one on. Yeah, you hit enter. All right. Let me zoom out for you. Yeah, I'll show you how to do it. I still don't think it'll zoom out properly. Yeah, hold on. I got to change my window. Window. What is my X-mins? Oh, keep that at like -10. 10. Y-min, I don't know, like -500. Wasn't that it? Yeah. 500. And then we'll go by a scale of like, I don't know, 50 or something like that. Let's see what that looks like. There we go. Yeah, there we go. That's better. That looks great. Okay, look. So see that point of inflection right there? At -2, 0. And then, so it's concaving up, then it concaves down, and then it concaves up. And that's